So welcome everyone to this first webinar of a series about photomonitoring that you will see also in the next few weeks or months. And first of all, some important information. As you can see, your microphones are currently muted, and you can write your questions in the chat, and we will answer at the end of the webinar. And also, I think the recording already started, and so you will also have the possibility to see again this webinar in a recording mode. We will let you know how to watch it. We will make it available on our website or LinkedIn. I introduce myself. I am Vera Costantini. I am business developer and project manager at NHAZCA. This is my colleague, Marco Fiorio, aerospace engineer, who will present at the end of, after my presentation, we'll do a demo of our web platform. Just for the people that do not know us, NHAZCA is a spin-off of Sapienza University. We are international leader in providing monitoring solutions with remote sensing technologies for land and infrastructures. Even if we are now, let's say, independent from the university, we keep collaborating with them in many projects. Also, we keep investing in research and innovation, and we have a highly diverse team of fully qualified graduates. But let's talk about photomonitoring. This is a monitoring technology that NHAZCA employs in many different projects. It was developed mainly to take advantage of the great availability of optical images that we have today and that are acquired by multiple platforms. It is based on digital image processing techniques, and that I will show you a little bit some of the technology behind, let's say, and all the algorithms behind. And it's also very scalable because it operates at multiple scales from large territories, if we think about the analysis of satellite images, but also at small scales like individual buildings. In fact, another characteristics of the technology is that it can use images from different sensors and platforms. As already said, there is an increasing availability of sensors that acquire images. For example, we all know that we keep a camera with us all the time with our smartphone. And in fact, for example, an estimation of 2022, there were more than 1 trillion of images were captured with our smartphone and also other kind of mobile cameras. And also drone and earth observation market are growing very fast as well. So what to do with all these images available? We can analyze these images for changes. So change detection, which is searching for features that change, that appear or disappear between one image and another, of course. And we can perform displacement detection, so detection of the movements of translations, rotations, deformations of features. But when we analyze and compare multitemporal images, we can face many different issues and problems. One of the main problems is that images often are not well overlapped or co-registered, and so they are misaligned. We can have differences in illumination between one image and another, and different environmental problems like rain, fog, clouds, but also moving objects. What do we mean? We mean objects in the view that we are analyzing, but objects that we are not interested in, like vehicles or animals, people that move, and we need to mask them to avoid the noise. So how do we solve these issues? Misalignment of images and illumination changes are solved with advanced algorithms, for example, co-registration algorithms, pre-processing algorithms that compensate for these illumination changes between images. So these changes that we do not want to analyze, we want to eliminate them to detect the real changes. For environmental noise, we can perform different spectral and statistical analysis. For moving objects, we can apply masks and filters in a post-processing step, for example. And how do we do this in our software, Iris? Here, for example, we see a short video that shows the software interface. And in particular, here we see the change detection analysis. This is an analysis between two satellite images. And the reference image is called master, and the secondary, let's say, image is called slave. We can have many slaves images. And the result is a change map in which we see in green the things, the objects that didn't change, and in the different, in the colors from yellow to purple, we see different levels of change. If we talk about displacement analysis or detection, this technique in Iris is very sensitive, because we can measure also displacements of less than the pixel resolution. So we can detect the movement of objects that add a movement of less than 1 pixel, because this information is present in the images, and we can detect with the right techniques. This is an example of, for example, a displacement after an earthquake, analyzed with the Pleiad images, so optical, multispectral, high-resolution images. And this is quite interesting, because with this analysis we can see, we can distinguish very well the fault along which the direction of displacement are exactly the opposite. And on the left, we see the resultant displacements, while in the other images, we see the north-south and east-west components of the displacement. Also, with displacement analysis, we can perform what we call multi-master or multi-image analysis when we have more than 2 images. The ideal situation is to have a stack of images, of multiple images. In this case, we can use every single image of the data set as a master and as a slave in a consecutive correlation cycles. In this way, the redundancy helps to increase the accuracy of the result. And as a result, we can also build and extract from every single pixel of the deformation map a time series that tell us about the movement of the single point in time, of course, and so the evolution of the deformation, of the displacement. And as I said, the data that we use for photomonitoring can arrive from different platforms and sensors, from webcam, from aerial platforms, from satellite. And on the lower left corner, we see, for example, an analysis performed with smartphone pictures of a landslide, and also from drones. And so we will see some real-world applications. For example, here I will show you some landslides and glaciers application. Here we see an example of a continuous monitoring of a slow landslide. So with a fixed camera that can acquire every 5 minutes, every 10 minutes, it depends on the need. And the result is, I zoom in a little bit, a deformation map. In green, we see everything that didn't move, And in the colored part, we see the different entity, the entity of the displacement. And the arrows, of course, indicate the direction of the displacement. And here we have a very similar example. In both examples, we can see that we also used a mask to isolate the landslide area and analyze only the part that we are interested in. And also we can, as I said, extract time series of every point that we are more interested in, for example. This is a similar example, let's say, with a slow landslide again, but the sensor, the platform is different because it's a webcam. And also we can say this is, let's say that the data, the input data is not very good quality, but still we can extract information and extract time series of the area and understand the evolution, the differential evolution of the landslide in the different part of the area, for example. Another example of slow landslide, but monitored with the drones. So in this case, we speak about periodic photomonitoring because the acquisitions were done like, I think it is like 5 acquisitions in a couple of years. The result is still possible to extract the time series, which will have just 5 points, but still we can understand the evolution of the phenomenon. This is very interesting, actually, at least to my opinion, because it's this glacier that moves, looks actually like a flowing river. Instead, it's ice, and it's quite, let's say, easy to monitor and follow the movement of the ice with, in this case, ISI images, so radar data, but we can have pretty much the same result with the optical image like Landsat or other also low resolution data. And in this case, we see a pretty homogeneous situation of the movement in the different part of the glacier. Okay. Another application for photomonitoring is rockfalls monitoring, which is, I would say, one of the most tested application, also because we use our leading laboratory, which is Poggio Baldi landslide, a very active rockfall, in which, in this case, for example, in this image, we see that with change detection, we can understand, we can see the precursors of the landslide. So the part of the scarp in which there was some detachment of rocks, and we can understand, this is an event. At the end of the analysis, for example, long-term analysis, we can identify the most active areas of the scarp. In this case, we apply, as I said, change detection, because actually what is actually detected are the detachment of the small boulders and rocks in the scarps. Here, another example of the same area. Other interesting application is the tunnel monitoring, in particular tunnel convergence. In this case, this application involves the use of 2 cameras positioned on the right and left sides of the tunnel to capture the ideal scenario. And during what we do is to monitor the tunnel convergence, which is normal during the excavation of the front. But of course, with this technique, we can assess if the tunnel convergence is in some range and threshold, which is safe, of course. So at every installation of the supporting arch, we do this monitoring. The images are acquired, and we can see, for example, here in this graph, that of course the displacement of different section of the tunnel and the highlighted periods are those related to the excavation front advancement, in which we see actually a displacement. There are many important infrastructures. Bridges are one of the most, I would say, important infrastructures, and it is important to monitor the structural health, of course. And one of the applications is, for example, to monitor with the changes in cracks, so the evolution and the appearance of new cracks, like in this example. And another example is the dynamic monitoring. For example, we put a fixed camera close to this bridge in Rome, and we were able to detect the displacement of the bridge, of an area of the bridge selected during the passage of the train. And so we could detect a very small displacement of less than 3 millimeters, and also to understand the natural frequency of the vibration of the bridge. Okay. Last application is buildings monitoring, which can be done, for example, as I said before, with the smartphones. This is, for example, periodic inspections on structures damaged after an earthquake. And this is a similar situation. In this case, we apply mostly change detection, of course. And because I want to leave some time to Marco, I will go to the last part of my presentation. And so how photomonitoring works. The first part is the image collection. If it's from the ground, as I said, it can be done by webcam or fixed cameras or smartphones, but it can be done from space, from satellites, or from drones. The second step is to transfer the data to the Iris cloud system, where the data are processed. And it depends on the source of data. The processing can be a little bit different, but the principle is the same. The web portal is used to deliver the results to the customer. And Marco will show you this portal with some examples that we have already in the web portal. We also generate reports, and also which can contain also some interpretation of the data if the customer, of course, is interested. But also receive, for example, instant messages or notifications in case of that an automatic threshold is set. When this threshold is overcome, of course, there is the possibility to have an alert received to your mobile phone. How do you access, let's say, to the service? First of all, most important thing is to understand what you need, what is your monitoring need. Then, of course, you can contact us in many different ways, via email or by phone, of course. You can also write to my email, which you will find at the end of the presentation. We define together the best solution for your monitoring need, and you will receive your proposal. Of course, you should be ready to answer to some questions. First of all, what is the size of the area, and which frequency of results you need? So multiple times per day or to one per year. What target size? So what are you looking for? What is the element that you want to monitor? And what kind of analysis you need? So change detection or displacement detection. And I think it's the end of presentation for me. So I leave the floor to Marco. I guess I should interrupt my sharing. Marco, the floor is yours.
Thank you very much, Vera. Thank you very much for your comprehensive introduction about the photomonitoring technology. Before delving into the technical aspect and the live presentation, I'd like to introduce myself very quickly. My name is Marco Fiori. I'm an aerospace engineer, and I'm working in the research and development division of the company. Specifically, my work is focused on the development of software and algorithms for photomonitoring applications. So while Vera has provided you with a, let's say, a broad introduction about the technology, focusing on the theoretical standpoint, I will follow a more hands-on approach by showcasing the actual results and some applications of our algorithm to real-life examples. And I'll do so by showcasing our interactive visualization platform that we have developed in-house that is used to convey the results of the analysis to our customers. So the web app can be accessed conveniently by any web browser. I'll be using Google Chrome for this example. It can be accessed by navigating to this address, iris.nhazca.com. The first time a user connects to the website is requested to create an account by clicking on the Register Here button. Once the account is created, the user can access the platform by inserting the credential in the fields and then clicking on Login. Afterwards, the user is presented with several choices depending on the scenarios that he's interested in monitoring. And for the sake of this live demo today, I'll be showing you both some applications of change detection, displacement analysis, and finally, last but not least, tunnel convergence. We'll start off with change detection, and I'll do so by illustrating the Poggio Baldi landslide. As Vera correctly said, just to give you a little bit of context, Poggio Baldi is probably one of the major landslides in Italy. It's probably one of the largest rock and debris phenomena. It is located in the Emilia-Romagna region in the Apennines. It's actually quite big. The main escarpment is 100 meters high and almost 250 meters wide, with an estimated volume of around 4 million cubic meters. The last activation occurred in 2010, and it caused a lot of damages in the private homes nearby. It is located close to the municipality of Corniolo, Santa Sofia. It also caused the damming of it's a natural damming of the river, the Bidente River. So soon after the event, NHAZCA decided to set up a lab in the area in order to develop a better understanding of the complex kinematics of the landslide. And we installed a lot of sensors. We conducted a lot of site surveys, geomorphological and geotechnical. We installed both contact sensor, like strain gauge, piezometer, inclinometers, but also a lot of remote sensing instruments like total station, laser scanners, synthetic aperture radar, and also cameras that we use to perform change detection. What I'll show you today is this interface that can be used to navigate the point of view. Basically, the user can zoom in, zoom out, can pan around, and can also cycle between what we call the source and the destination image, or the primary and secondary or master slave, if you want, in order to better understand the results. There's a slider in the bottom part of the interface, which allows the user to focus on a specific time frame of the dataset. You have to consider that this specific dataset was acquired approximately over the course of 1 month, from the 24th of May 2024 to the end of June. The specific time frame that is in focus can be checked in the lower right portion of the screen. And whereas it's kind of easy to spot big changes, so a big detachment of rocks by naked eye, I challenge everyone to do so without the aid of photomonitoring for smaller rocks. You need to consider that this portion of image is highly zoomed. And I'll show you that the software is actually quite effective into spotting small detachment of rocks that would be otherwise extremely hard to spot by naked eye. As Vera correctly said before, this is a visual representation where a heat map is basically overlaid to the original image. And the green color denotes little to no change, whereas red, purple represent maximum change. But of course, we can also deliver numerical results, analytical results, both in terms of a matrix, which represent for each pixel the amount of change, but also we can deliver some sort of more complex analytics in terms of where in the image the changes are located. So the position in terms of pixel, the amount of area, and so on and so forth. Another interesting example is Tor Giovanetto, which is a disused quarry in Italy, close to Monte Subasio in the region of Umbria, close to Perugia. This is affected by a large sliding wedge, which is in the process of dislodging and is endangering both provincial road and a state road below. So we have installed the camera here, and we have tested our change detection algorithm on the site. And you can see that these images were acquired approximately 6 months apart. You can see in the lower right portion. The first image, so the master image, was acquired on the 23rd of May 2024, while the second image was acquired on the 5th of November 2024. And we were able to spot big detachment of a boulder here and the gravel that was created underneath. You can see the primary and the secondary image, and this is the result of change detection. But this example is particularly useful also to show you the vegetation filter, what we call vegetation filter algorithm, that can be extremely useful in scenarios where there's a lot of grass, there's a lot of shrubs and foliage, vegetation that could otherwise create noise in the process. We filtered this out by sort of masking out all the portion of the images which have a certain content in terms of color and bandwidth, which is, let's say, we filter out the portion of the images that have a bandwidth in color which is close to the green. Last example that I wanted to show you is the landslide in Biricuccola in Emilia-Romagna. This is a slow landslide that Vera showed you before in the presentation, and I can show you the data set here was acquired over the course of approximately 3 weeks from the 8th of March to the end of March 2024. And also here, the results are pretty neat. I'll show you now a couple of time series. This is the horizontal displacement, very neat. Here and here. Now, last but not least, let me spend just a couple of words about tunnel convergence. The interface here is a little bit more comprehensive because we have a picture of the tunnel. As Vera correctly described, what we're doing here is we're trying to describe the convergence of the internal walls of the tunnels. And to do that, we made some assumptions, basically. So we make the assumption that the tunnel can be modeled as a cylinder. And then what we do is we track the motion of the pixels in the frame, in the picture, and then we intersect the rays coming from the optical center and to the internal walls of the tunnel. And then we compute the displacement for each section, what we call progressive, that you see here. Usually there are 1 meter apart. So what we see here in the result, we have the possibility to change the camera position. So for each section, we can choose the right or the left camera, and it is represented here. We have a visual representation of the arcs because you have to consider that the results are averaged on a certain number of arcs. So we consider a certain number of points and we average the result in a sort of arc section. And then we have the time series of displacement. And we can use the same scroll bar at the bottom to move, to basically navigate each section. What's interesting here, as you can see in the lower left portion, where there are the source images, sometimes the scenery can be obstructed by machinery or by like powders or some other substances in the air due to the work in progress. We basically rely a lot on redundancy. So we are able to sort of filter out the noise by combining a lot of different images which are acquired with high frequency. And that allows us to monitor section of the tunnel that are partially covered by machinery or other obstacles. And also we are able to track the work as they advance, in the sense that as when the sort of the excavation walls get farther and farther from the camera, we can, what we do, we basically move the camera and then we link the new data to the previous one in order to create a continuous data set of information. And we can scroll through the entire data set. This was tested in Italy, in Valfabbrica. And again, I can also change between the two, cycle between the two components, horizontal and vertical, time series I've created for them. When you see blanks, it means that we didn't have the data. And it's not shown here actually, but the results were compared to the telemetry data acquired on site, and we found a very great matching. And especially we found that the basically when you see a rate that is different from 0, it corresponded to the moment where the excavation were in progress. So this is an extremely useful technique, which has a lot of advantages towards common, let's say, telemetry data, because it reduces the risk of the operators, since it is completely remote and it doesn't require anyone to actually go close to the excavation wall. So these end the live demo demonstration of the visualization platform. Of course, if you have any sort of question, me and Vera are more than glad to answer and to provide you with a satisfying answer.
Thank you, Marco. So thank you, everyone. Thank you, Marco, and thank you, Lorenzo, for the housekeeping organization. And we will keep in touch and we'll let you know about the next events.
Yes, we're looking forward
everyone.
to seeing you for the next appointment of this webinar session. Thank you, everybody.
Thank you for joining us. Bye. Bye-bye.
Bye-bye.